What if I told you there's a way to make your AI requests 10 times cheaper and up to 85% faster? It sounds a little bit like magic, right? But it's totally real, and it's all thanks to a surprisingly clever trick that the biggest names in AI are using right now. So how on earth is this possible? Well, today we're pulling back the curtain on a technique called prompt caching.
First, let's just let that number sink in. 10 times. For massive AI providers like OpenAI and Anthropic, the input tokens you send that are cached are an absolutely staggering 10 times cheaper than the standard ones. I mean, this isn't just some small discount. This fundamentally changes the math of building with AI. It makes applications that were way too expensive just yesterday suddenly possible.
And you can see it right here. The visual says it all. The difference in cost is just massive. But it's not just about the money. Anthropic also says this can slash latency. That's the time it takes to get that first word back, by up to 85% on really long prompts. So it's cheaper and it's faster. So what's the catch?
And that, right there, is the central mystery we need to solve. If you send the exact same prompt to an AI multiple times, you get a different answer each time. We all know that. And yet, the system can still tell you it used a cache. So it's obviously not just saving the old response. To figure out what the AI is actually remembering, we got to take a quick peek under the hood.
Think of this as our roadmap. On a super high level, a large language model chews on information in these 4 stages. It starts with the tokenizer, then it moves to embedding, it does all the real heavy thinking in the transformer, and finally, it gives you an output. The secret to all this caching magic? It's hiding right in the middle, in that transformer. But to really get it, we have to start at step 1.
So first up, the tokenizer. You see, an AI doesn't read words and sentences like you and I do. It reads numbers. The tokenizer's job is to take our prompt, chop it up into these little chunks, we call them tokens, and then assign a unique ID number to each one. These tokens are the absolute bedrock for everything that happens next.
For instance, a simple phrase like check out ngrok.ai gets crunched down into this string of 5 numbers. And look closely. See how ngrok.ai itself gets split into 3 separate tokens? The key thing here is that the exact same prompt will always create the exact same sequence of tokens. The human world of language has just been translated into the machine world of numbers. Okay, so now we have our numbers, but right now they're just IDs. They don't have any actual meaning on their own. That's where the second stage, embedding, comes into play. Think of it like this. Each of those token IDs gets looked up in a gigantic dictionary. But instead of a text definition, it gets a super complex set of coordinates, an array with thousands of numbers. These coordinates pinpoint the token's location in this vast, multidimensional space of.
This is such a critical step. We've gone from a simple, one-dimensional ID card, that's the token, to this incredibly rich, complex GPS coordinate for what a word actually means. That's the embedding. And what's cool is that words with similar meanings end up being close neighbors in this crazy high-dimensional space.
So now our words have individual meanings, but language is way more than just a list of words, right? Context is everything. So how does the AI figure out the relationships between all the words in a sentence? Well, the answer lies right in the heart of the model, the transformer, and specifically a process inside it called the attention mechanism.
I want you to imagine the AI is at a big cocktail party. As it hears a new word, it looks back at every other word it's already heard. It then decides how important each of those previous words is to understanding this new one, giving them each a little attention score. Then it blends all those past conversations together based on those scores to get the full picture, the full context.
But here is the massive, huge inefficiency. The way it usually works is that every single time the AI generates one new word of its response, it has to rerun that entire cocktail party calculation for the whole prompt, right from the very beginning. As one of our sources put it so perfectly, we're redoing lots of calculations we don't need to. And this is exactly where caching swoops in to save the day. The old way is just brute force. You recalculate everything every single time. It's slow and it's expensive. The new way, the cached way, is all about being smart. You calculate the context of the prompt just once, you save the result, and then you just build on top of it. Now, the secret sauce to this smarter way is hidden in the math of that attention mechanism. Don't worry, we're not going deep here, but the process creates 3 things from the embeddings: a query, which we call Q, a key, which we call K, and a value, V. Just remember those 3 letters, Q, K, and V. And there it is. That's the solution to our mystery. Prompt caching is really KV caching.
The thing that the AI is remembering between your requests isn't the text, it's not the final answer, it's the calculated key, the K, and value, the V, matrices. These matrices are basically the pre-chewed, context-aware meaning of your prompt, all ready to be used again.
So let's walk through how this actually works. It's pretty simple. Step 1. The first time you send a prompt, the model does all the heavy lifting and calculates those K and V matrices. Step 2. It saves them to a cache. Then, the next time you send a request that starts with that same prompt, it just loads the pre-computed K and V straight from the cache. And finally, it only has to do the new math for whatever new words you added. All that repetitive work is just gone.
What's really interesting is that different companies do this in different ways. OpenAI kind of handles it automatically, behind the scenes. That's easy, but it can be a bit inconsistent. Some tests show it only works about half the time. Anthropic, though, does it differently. They give developers direct control, so you can explicitly tell it to use a cache. And when you do that, you get a predictable 100% hit rate.
So this all brings us right back to where we started. By saving and reusing those K and V matrices, we get to skip a ton of redundant calculations. And the result? You get that dramatic drop in latency, especially for long prompts. You get that 10x cost reduction for your input, and, at least with some providers, you get much more predictable performance.
And hey, here's a super important little detail for anyone who's actually building with these APIs. You might be thinking, wait, what if I change a setting like temperature to make the output more creative? Won't that break the cache? And the answer is, no, it doesn't, because those settings get applied after the whole attention and KV caching process has already finished. So you get the full speed and cost benefits while still having total control over the creativity of the response.
So this all leads us to one final really powerful thought. KV caching isn't just some minor little optimization. It's a fundamental shift in the economics and the speed of interacting with AI. And that raises a really fascinating question for all of us to think about. As this core part of AI gets dramatically faster and cheaper, what completely new kinds of applications and experiences are suddenly going to become possible?